This is the identification of sodium carbonate or sodium bicarbonate lab. In this lab, we are going to determine the identity of salt A or B that could either be sodium carbonate, washing soda, or sodium bicarbonate, baking soda. And so to begin, a known amount of each of these salts will be measured and then reacted with 3 molar hydrochloric acid. And in the process of this reaction, the products will be CO2, sodium chloride, and water. We will drive the reaction to completion by adding excess 3 molar hydrochloric acid until the visible bubbling subsides. Once all the bubbling has subsided, we will visibly know that we have driven the reaction to completion. From this point, we will evaporate off the water to reclaim the dried sodium chloride. We will mass out that dried sodium chloride, and from that experimental mass of sodium chloride reclaimed by the evaporation of the water, we will determine whether we have salt A or B, either sodium carbonate or sodium bicarbonate, by using stoichiometry from our original mass of our salt. So from our initial measured values of salt A or B, we will stoichiometrically calculate how many grams of sodium chloride we should produce. So it's really important that you write the chemical formulas properly, and of course write the balanced chemical formula. Of course, we're dealing with sodium hydrogen carbonate or sodium carbonate, and they will both react with excess hydrochloric acid to produce CO2, sodium chloride, and water. They have very similar reactions. However, there is a slight difference in the stoichiometric coefficients that will lead to different amounts of sodium chloride that we can determine from which salt we started with. Therefore, the amount of salt that we obtain experimentally will help us identify the original salt that we started with by using our balanced chemical formulas, our chemical formula writing, and our stoichiometry. Let's begin. So let's begin by measuring our empty and dry evaporating dish and a watch glass. And the watch glass is used to help collect any splattering salt that may occur as we heat the salt water. Okay, now I'm going to add salt A. That could either be sodium carbonate or sodium hydrogen carbonate, sometimes called bicarb. And we're going to take the value of this one. So we have the dry evaporating dish with the dry evaporating dish with the watch glass, and now we have the evaporating dish with the product and the watch glass. Subtract out the difference and you have the mass of your initial grams of A. Now we'll mass the empty evaporating dish with its watch glass, and that's the empty. Write that down. And now we'll add some reagent B, which could be the sodium carbonate or the sodium bicarb or sodium hydrogen carbonate. And of course, we're going to measure it with its watch glass. That's the value we need now. And we're going to, of course, subtract that from the empty evaporating dish and watch glass to get the mass of the initial reagent B. And that's an important initial value that we're going to use to do our pencil and paper stoichiometry to obtain the theoretical amount of grams of sodium chloride that should be produced. Okay, now we're going to do the chemical reaction. And we're going to use our 3 molar hydrochloric acid. And we're going to add enough to A and B in order to drive the reaction to completion. And we know the reaction goes to completion when no more visible bubbling occurs. That means no more CO2 is produced. And there's no more visible bubbling. So, and I don't see, there's a little bit of bubbling, but I don't see any solid in the bottom of that. Okay, let's do chemical test B. And then as you can see, there is some fizzing that occurred, so there might be some loss of sodium chloride. And I'm just going to keep adding the hydrochloric acid. And certainly 1 molar could be used, but you're going to use a little more volume here. Again, that fizzing is decomposition of the carbonate ion, becoming CO2 and water. And you know that you've driven the reaction to completion when the fizzing is stopped, and you can clearly see no more visible solids. I'm going to add a little more just to make sure we have driven this reaction to completion. The hydrochloric acid should be limiting. It's taking a little more hydrochloric acid than the other reagent that might be a telling sign of what salt this possibly could be. Or was it a mass difference? Okay, no more visible fizzing. Okay, so I have driven the reaction to completion, and now I have essentially sodium chloride solutions here. And we're going to have to measure out our dried sodium chloride, so now we're going to heat. Now also, we probably most definitely have excess hydrochloric acid that we will also boil off, as hydrochloric acid actually is a gas dissolved in a liquid. All right, so now we're going to turn our hot plate on. And we're going to place our saltwater solutions in evaporating dish on, and we're also going to place the watch glass. And the whole idea here is to prevent any splattering, loss of the salt as I heat. You certainly could heat a lot slower and do without the watch glass. But it's nice to be able to do this in a period, if you can, in the classroom. So I'm going to heat and turn up the heat. So I'm going to turn the heat off, let these cool before I mass them out. And you can see the reason for the watch glass, as we can see the beautiful sodium chloride crystals that have developed inside the evaporating dish and also on top of the watch glass. Now that our evaporating dish and watch glass is dry, we're going to make our final measurement to get the mass of my sodium chloride. And that's 99.70 for A. And we can see these salt crystals in both the evaporating dish and watch glass. This actually is stuck onto it. It's kind of cool. It precipitates the salt kind of is now stuck there. And so B, evaporating dish and the evaporating dish and the watch glass for B is 97.10. And again, same idea. If I can just get this open, you can see the beautiful crystals here of the sodium chloride.